How does something like the amount of protein that is found inside of the blood affect fluid dynamics, affect blood pressure, affect how much fluid's inside of the tissues? Now, before we get into it, if you haven't watched the video on osmolarity, I recommend you do that. And if you haven't watched the video on capillary exchange, I recommend you do that. But let's go ahead and get into it.
Okay, so we have to remember that we are going to be working inside of a closed system. So let's imagine that we have a closed system and we go ahead and we put some fluid in there. Let's call that fluid water. So that's going to be our little like water droplet here. Okay, so that's water inside of our closed system. Now imagine that you put water inside of a closed system like a balloon. As you do so, that water is going to exert force on the walls of the closed system, just the fluid itself. And that is what we refer to as our hydrostatic pressure. Okay. Now, we can also take and we can put stuff inside of our water. Okay, this could be ions, could be carbs, could be proteins, right? But we're going to put stuff inside of that water and we're going to dissolve that stuff, right? And that stuff is what contributes to the osmolarity of the water, right? So how much stuff is in there. Now the stuff wants to be diluted. So what's going to happen is it's going to want to pull water from outside sources into this closed system because it wants to be diluted, right? So it wants to drive the osmolarity down, and that force is what we refer to as osmotic pressure. Okay? And it wants to pull water in. Right? Now imagine that we put our closed system that we just made inside of another closed system, and inside of this secondary closed system, we're going to put fluid. We'll put water. So there's our little water droplets. Okay, now that water, right, is going to exert force on the walls, but it's also, if we put our water droplet over here, is also going to exert force on that secondary closed system on the inside, right? So this here, this is a hydrostatic pressure. Right. Now, let's imagine that out here we're also going to put stuff. Put our little macromolecules and our ions out here in this closed system. Okay. Now, what it's going to do is it's going to want to pull water out to dilute itself. Right. So the stuff wants to be diluted. Okay. So this is an osmotic pressure. Okay. So now notice that we have two hydrostatic pressures and we have two osmotic pressures, right? So if I zoom out a little bit, move this up, what we can see, right, is that we have a hydrostatic pressure, okay, here, right? So let's imagine that this is our capillary. I'm just write cap here, and this is the tissues. Okay, so we have a hydrostatic pressure of the capillary, okay, and that is an outward pressure. Okay, we have a hydrostatic pressure of the tissues, and that is inward. If we think about the capillary itself, it's pushing into the capillary. Okay, then we have an osmotic pressure of the capillary, right? Look, there's the osmotic pressure of the capillary here. Okay, and that is an inward pressure. And we have an osmotic pressure of the tissues, and that is pulling it out of the capillary. So that's an outward pressure. Okay, so now if we want to figure out our net filtration pressure, okay, we're going to take our outward pressures, which is the hydrostatic pressure of the capillary, that one, and we'll add the osmotic pressure of the tissues, And those are two outward pressures. So this is out. Then we take and we subtract our inward pressures, which is the hydrostatic pressure of the tissues plus the osmotic pressure of the capillaries. Okay, so these are inward pressures. So we have out minus in, and that is equal to our net filtration pressure. Now, if we modify these in any sort of way, right, that will lead to changes in our net filtration pressure. So let's say that we increase our hydrostatic pressure of our capillaries, right? That's going to make this number bigger, which makes the net filtration bigger, okay? What happens if we now start to mess with the content of the blood by adding in or taking out proteins? So let's take out proteins, okay? If we are going to take out proteins, right, what's going to happen is we are going to get rid of this stuff or reduce that amount of stuff, okay? And that is what contributes to the osmolarity of the blood. It's going to impact this pressure here, the osmotic pressure of the capillaries, right? And so if we have less stuff, we have less osmolarity, less drive to dilute it. So it's going to take that osmolarity and osmotic pressure of that capillary and it's going to decrease it. Okay, so now what happens is that number goes down. Okay, so if this number goes down, what happens to my net filtration pressure? My net filtration pressure, right, because this number is lower, is going to go up. So if we decrease the amount of protein in the blood, the net filtration pressure goes up, right? And this net filtration pressure, out minus in, if it goes up, that's going to lead to drive water into the tissues. So we have more water in the tissues, right? And so that's going to lead to something like edema, water sort of pooling in the tissues, right? Now, but one of the things that we also have to keep in mind is that if we look at our capillary, right, it's a blood vessel, it's a tube, looks sort of like this, right? And blood moves through the tube like this. We have a net filtration pressure on the arterial end, and we have a net filtration pressure on the venous end, right? And we know that here at the arterial end, it's pushed out, and we know at the venous end, it's pulled back in, right? And so what's going to happen is that this osmotic pressure of the capillary, right, will impact both it on the arterial end, but it will impact it on the venous end. So what you need to think about is how do these pressures look on the arterial end and how do they look on the venous end? Because it can impact not only the drive of fluid out of the blood vessels, but it can actually also impact the drive of fluid back in. So osmotic pressure in the capillaries, this inward pressure, right, helps with bringing that fluid back in down here on the venous end. Because of that, we have less brought back in, right, on this venous end. If we have less brought in on that venous end, what's going to happen is we have the same amount, if not more, pushed out on the arterial end, less brought in on the venous end, so that means that more remains in the tissues, right? So now what I want you to do is I want you to go try and see what happens if we increase the amount of proteins inside of the blood and see if you can figure out what happens using just this equation here and working through that process. If you have comments or questions, go ahead and leave that in the comment section, and I'm happy to help you out. Later.